Howdy, everybody. Hope you're doing well wherever, whenever you are. We're here for day 15 or quest 15, I guess, because it's not day base, but quest 15 for Everybody Codes. And I think this day went pretty well for me. I actually finished it last night, so I'm recording the next day. But I wanted to try and do some refinement and like talk over my solution a little bit. And so I did some diagramming and I tried to do a lot of refactoring. My original solution was kind of a mess because I was trying to like figure out like where it looks, and I wasn't doing a very good job of like intersecting and stuff like that. So anyway, you'll see what that looks like. But I did think it would be good just to kind of show you how to do this, because I know this is a one that I've done in the past that I've like struggled with. So maybe you've struggled with it as well. And so to really deep dive into it and to understand the intuition, I think will help a lot with other puzzles like this. So this one is called Definitely Not a Maze. And it's actually, the first two parts aren't that hard, but it starts out with the idea being is like, you've freed all the dragon ducks, your friends, and now you're trying to escape, but you can't escape back where you came because it's all blown up. And I think you fell through the wall or fell through the floor, but you can use echolocation to find walls. And so that's your puzzle input is the echolocation, and that's kind of how it works. So anyway, let's just get into it. I love your comments, by the way, so please keep them coming. I love reading the Reddit from previous days. I haven't read today's, so we'll see what happens with today's. So what does it say for part one? Basically, you're going to be given a set of instructions that are like your what your echolocation produced. And we've done things like this similar. Basically, you're going to be told whether you want to turn left or right, and then how many steps you need to walk. So the idea is, you know, for this first case right here, you're going to turn right and then walk 3 steps, and then you're going to turn right again and walk 4 more steps, and so on and so forth. And that's going to, so this example is going to produce this right here. And these are the walls. So your echolocation has like followed the wall path, and these are like the walls. And the very first position where you start is the start, and the very last position, so the 9th value here on this last 9 one right here, is going to be your end position. And then the question it asks you is, can you find the shortest path? Okay, so that part probably shouldn't be hard or new or different to anyone. We've done a lot of shortest path algorithms before. You might even say to yourself, oh, shortest path, because everything is 1 step, I can just do BFS, right? Presumably, like branching with a BFS eventually gets you to the shortest path. You know, you might say to yourself, oh, could I do some kind of A star algorithm where you kind of do a Dijkstra with a heuristic, where you say like, oh, I should prefer nodes that get me closer to the position. So those might have worked. I think for part 1 and part 2, it's easy enough just to do a breadth first search. Solve that. Anyway, they give you a larger example. Although I will admit, like, this example isn't super helpful because like it draws a pretty small grid, and it's fairly obvious that you just like, here's the fastest thing, or here's the fastest path. Is like its 16th segment, right? So here's the fastest path. It would have been nice if there were more twists and turns, I think, because it helped me think about, I actually had to look at the other puzzles to like get a better idea of like what it looked like. I'll show you that in a second. But again, you're really just doing the shortest path is the idea, right? You're going to draw these walls, you're going to build the walls out of your thing, and find the shortest path. That's all you have to do. So you can see the input is a lot longer, but all the numbers are fairly small, so they're just 1 digit. I should say, at least for my input. So what do we do? This time I decided to use a point I think originally in part 1 and part 2 I did not use a point because it was easy enough just to like keep track of rows and columns, but you'll see later in part 3 it was much more complex. But excuse me, using a point allows me to do some additional math. Oh, before I get there, I should probably just talk about the parse input. From a previous comment, someone had mentioned you can split at, and I think that was really cool. So I use that here, right? So we know it's like one character is left or right, and then the rest of it is the number. So you just split at 1, and then that gives you your first character, and then the rest of it you parse as I did I sizes, because you're going, this is I think you treat it truly like a Cartesian plane or whatever, you know, the XY axes, because you want to like, you start at like, say you start at 0, 0, maybe you go down, but you'll definitely get way up here, and you can definitely get way down here. You can go way all over the place. You'll see in part 3. So I'd used I sizes here for all of my points because I figured, oh, it'll go in different. But then I just implemented add for point to point and a reference point to a point. And then I did an add assign, I think, because later as I was refactoring the code, there was a plus equals that made it easier to do that. And then I did scalar multiplication, which you'll see me use in a second. I also implemented, you know, a new just to make it easier to create it. And then a turn, which is like give me a new point when I've turned. So if I'm, think about it like if you're in this direction and you turn left, go this way, I guess it depends on how the camera is, but like the idea is you're going to turn left. And we had a problem like this before, and a commenter, again thank you, had pointed out that you can the way that you turn is you just swap the x's and y's, and then if you're turning left you negate the y, and then if you're turning right you negate the x. So that's what we do here, right? We just swap the x's and y's, negate the x's. I had to think about it the first time I did it, like some intuition on like how does that work, why does that work like that when you're turning left and right wherever you are. But it made sense. I remember to do it, and I think I understand a little bit better, so it was a little bit easier to remember to do it like this. There you go. So that's the point implementation. The next thing you have to do is like build the wall, right? Build a wall. So you're going to receive those turns where you want to turn, and then how far you want to go. And so that's all we do here is we have a wall. We start at 0, 0, and we start facing up. I actually don't think it matters where you face, because wherever you start facing, you're going to draw the map the same way. It will just be rotated, and so your solution to the problem doesn't change. You'll get the same output, but I think in this problem they start facing up. Yeah, because you like turn, so you imagine you're facing up, you turn left, and then you walk 6. So I just did that so my grids look similar to theirs as I was testing. I think I've since removed all the printing from the grids. I tried to clean this up, make it more readable. But you can imagine it being fairly easy to do a print. You like find the min max of the walls. The rectangle of the walls is what I did. And then I just did a for loop. And I was like, is the wall in the hash set? If it is, put a hash, otherwise put a dot. And then I think I did some extra logic for 0, 0 being the start and the end. Okay, so but how do we build the wall? Basically, we turn. So given our direction, we turn. And then for each position from that distance to, or from that position to the distance, we add a wall. And this is where the scalar multiplication and the addition come in handy. Because I can just say, hey, at insert cur plus delta times v. And so that's going to slowly build up a wall going in that direction. And then I just need to update my current position to be delta times the distance I go, right? So I do that, and now I have a new, now I'm facing a new, now I'm like at the end of it, so that when I loop again, I can do the turn and draw around. One small bug I had when I was first doing the first part, I should say the first two parts I did like on and off. I had stuff I had to do, so I'd like come to it and go back and forth. And one bug I had that I was kind of thinking about is like, at first I couldn't find the end. My algorithm wasn't ever finding the end. It was coming with no solution. And by the way, if you aren't paying attention, that can actually run forever. So but the issue is I had not removed the end. So the end was considered a wall, so it was never being added to my like frontier, my to-do set. Anyway, that's just a key thing to remember is like once you've like built up the whole thing, the very last position is the wall, so you need. So but what this build walls thing function, it just returns the walls and it returns that end point. So you know you're always starting at 0 0, and then you're going to have some end point you need to get to, and then you're going to have a list of all the points that are walls, and that will help you infer your decision. So what do we do for part 1? Well, we build the walls, and then we're just going to do a BFS, right? A breadth first search. You could use Dijkstra's here. Again, because it's a distance of 1, Dijkstra's essentially becomes a breadth first search. I think I actually used the pathfinding crate in P3, so you'll see how that works. You could just as easily have used that, and that would have worked just fine. I think I did the BFS here because I wasn't sure. I actually don't know why I didn't do it, because you could potentially have just used the pathfinding crate. It's probably that we had implemented BFSs so many times in previous problems that I was just like, okay, here's another BFS. I'm getting my BFS reps in, right? How do you implement a BFS? Well, you want to keep track of the items you've seen before. Obviously, you don't want to visit a node you visited before. That is a key difference to Dijkstra or a generalized fast shortest path algorithm. Because we're only moving one step, we know if we've seen it before that we've already gotten there in a shorter distance. In Dijkstra, your seen list is actually different. You'll keep track of like what you've seen and how long it took you to get there, because if you do find a shorter path to that point, now you want to keep that up, right? Or just, I don't know, maybe not Dijkstra, but it just in pathfinding in general. You keep track of your scene list, and then you keep track of your frontier, which is like your work to do, like where you are. And then you just loop through it until you've either found the end or you've gone through it all. And if you've gone through it all, that means there's no solution. You couldn't find a path. So what do? I just loop through it, get that value in my distance, and I say, hey, is cur the end? If it is, then I just return the distance. Otherwise, I'm just going to loop through all the deltas, right? So I did this way. Sometimes I put a const up here. I don't know. You tell me how you feel about it. Sometimes it's easier to have it as a const, so it makes this part more readable. Sometimes this feels a little fuzzy, but I don't know. It felt okay to me with some. I just did it this way. So. But what do we do? So we do our cur plus our delta, which is our for loop. And then we want to make sure that neighbor's not a wall. And we haven't seen it before, right? And if those two are the case, then we add it to our like to-do list, our frontier. And that's BFS, right? You just keep doing it. And the sentinel case or like the exit case is this case, right? Did I find the end? Presumably, I just did unreachable because we're doing problem solving. Here you might return none if you were doing it in real life, and this would return some distant. Different algorithm, it's different too. Like some of them want the path, so you might actually be tracking the path. You'd return that too. That's what the pathfinding algorithm does. It gives you the exact path to get there. Anyway, so that's it for part 1. Again, it's just the maybe the hardest part of it is how do you build the wall, and then you just do a BFS. If you've done a BFS before, it should be same thing, right? At least for me, it was. That's how I solved it. I guess I don't know how other people solved it. Part 2, it said the grid's larger, so just do it a little bit. So do it again. This was the thing. I was all like, oh, why do I copy and paste? Why don't I just call P1 with the input for P2? So I did that, and that it solved part 2, right? I guess I should click this thing. So for part 2, it literally doesn't change, right? I think it even said it's like you tells you a little bit about the story, which is interesting, right? I'll let you read it. But I think it's making you more legendary and epic, and I thought that was kind of cool. Anyway, but it's basically saying you now have a grid and it's much larger. One thing of note, I used the split at, so I didn't have this problem. But before, I've had things where I've said, oh, just the first one is the turn and the second one is the integer. This one, and especially part 3, had like multiple numbers, so if you may have had to like make changes and update it to that. It's a good reminder, especially part 3, which we'll talk about in a second, to look at the actual input. So you can see the numbers are only slightly bigger, but there are a lot more of them. So I did look at that briefly and say, okay, there's a lot more, but it feels like it should solve. And you can see like the first one solves in microseconds. This one takes 15 milliseconds. It didn't feel that bad. So I just stuck with this and I did it. So that was part 2 for me, at least. I did use, because part 2 was like substantially larger than part 3, when I was like doing my iterating, I thought like, oh, how do I maybe I should test my P3 implementation on P2 just to make sure it worked. But I kept this here just so you could see how it looked. When I was doing that iteration, I just like took the P2 input and fed it into my P3 so I could see what happened. Part 3, what does it say? It's more story, which again, very cool. You're almost at the exit. There's one more room you got to get through. It does say one thing: the wall must be truly long, but just like before, it definitely doesn't intersect itself at any point. I think that was a hint, and it took me when I read it, I was kind of like, oh, that's clearly saying that the wall segments don't intersect, so you're not going to get weird paths that you would never be able to get to. In the end, I don't think it matters that much, but anyway, my first thought was, okay, it's much larger. What if I just run my P1 solution on P3 and see what happens? People, that is a bad idea. Look at these numbers. They're enormous, and there's a lot of them. And if you remember, I was building a wall for each point along this path, right? So just this one segment right here was creating 3 million points to put into my thing. We were fortunate I wasn't recording at the time. I would have lost that recording because I wasn't paying attention while it was running, and I was kind of like looking at the input and looking at the solution and trying to think like, oh, can I try? I think at the time I was trying to print it, and suddenly my computer slowed to an almost halt. And it's because I had allocated all 128 gigabytes of memory that my computer had, and it was not happy that I was asking for more, so everything was swapping and stuff like that and having problems. So it was a reminder to me to check the input, make sure you're not going to do anything absurd with your algorithm, because I was just making millions upon millions of points and storing it in an enormously large hash set. And it basically crashed my computer. It didn't crash it. I stopped the program. Fortunately, I'm back on Linux, and Linux does a good job of like managing swapping, and so things came back to life, and I was able to continue. But that was kind of a funny thing that I had, I bought 128 gigs because at the time it felt like, oh, I'll be doing lots of cool stuff. But I don't think I've ever used, even when I've had like 3 or 4 virtual machines running to do like some weird testing, I don't think I've ever even gotten close to it. But this was the first time, so quite a funny thing that I did. Oopsie. Anyway, the point of all of that is the problem is much bigger. And I created a thing here. After we were done, I got some help from AI to draw it. So you can see it right here. Like, this is the grid, but you can see the range is e to the 7. So this is like -4 e to the 7. Like that's the range. It's quite large, right? So you're drawing, these line segments are huge, and like here's the start position and here's the end that you want to get to. So how do you solve this problem? Even if you potentially, let's say you thought of an algorithm where you said, oh, I can, instead of building the wall, I'm just going to maintain the wall segments, and then I'm going to run an intersection algorithm to make sure that like my point wouldn't intersect, my movement wouldn't intersect with a wall, which you see that I do. I'll do that later. You'll see that I do that. I think that's, you kind of have to do that for like the am I in a wall type thing, or do I hit a wall? You still, the graph is so big, it's just infeasible for you to do Dijkstras, because there's literally billions of ways that you could go, and it would, you do billions upon billions upon billions of iterations before you actually reach the end, and it would just, it would take forever to finish, right? So in that sense, I think the idea was, you need to come up with something better. And this is actually a problem that we've had before in videos that I've recorded, I think. And I'm trying to remember the name of it. I think it's called something like, what is it called? Like graph contraction. Or like, I don't know. The idea is like, what it's really saying is there some easier way for me to simplify the movement? Did I lose my thing? Why won't you move, buddy? What did I do? Okay, here we go. Apparently I don't know how to use this program. Okay, I think it's called like graph contraction. Maybe you can help me. I actually tried to look after I solved it at competitive programming. I couldn't really find a good entry to describe it. So if you have some description that might help, the gist of it is, there's no need to try every single point. The way to think about this problem is, if I'm right here, there's only so many ways I can go, right? I can go down to here, I can go down over to here, I can go over to here, but you wouldn't want to try those like one at a time, right? You'd really want to go like large swath, go to here, and then you'd want to like large swath try to go to here, or maybe large swath try to go to here, right? Like there's like a fewer number of like points of interest, is what I call it, that you're actually interested in going in. And it looks a little bit like, let me zoom in. Sorry, that makes it a little bit uglier. But imagine you're like you're here at the start. You should ask yourself, like, where do I actually want to go? Where would be interesting places to go? And for me, it felt like it's these corners right here. So let me add something. Like these corners right here are like what feel like the interesting places to go in that corner. And same thing with right here, right? Like this corner, this corner, this corner. And I think I actually do this one too. So like each corner, each end of a segment produces like quote unquote 4 potential points of interest. Same thing with this one right here, right? You're interested in this one, this one, this one, this one, and this one, right? I'm not drawing it very well, but as opposed to saying, oh, I'm interested in like every point on this line, which there's literally millions of, you instead say, oh, I'm just interested in these points of interest. And that makes the graph much smaller, and that's how it helps you solve it, right? You're no longer thinking about the grid as moving one point at a time. You're thinking about the grid as moving in the interesting point. The gotcha to this is your points of interest have to actually be valid points of interest, because if you miss a point of interest, like maybe you say, oh, I'm only going to consider the outside corner, that may not actually get you the correct solution. So you do have to make sure that you have enough points of interest that you can truly make the graph accessible. And so there's a couple people I've seen people before do these like different ways. There's like an X's and Y's one that I don't totally understand. I think it has to do with the idea of like your you're drawing like lines like this along all these things, and then you're drawing lines like this, and wherever they intersect, you consider those like the quote unquote points of interest. For me, these ones, it's often easier to think about like the corners. So like whenever you're walking, you're almost certainly going to walk to a corner. And the reason is, the intuition behind that is, the only way you'd ever get around the grid is by taking corners, right? So the shortest path to get there, like you would never, to get down here, you would never, like, if say you're right here, there'd be no reason for you to go like this, right? You'd for sure want to like take the corner and then take the corner to get there, right? That would be the shortest path. And so in that sense, like, the question is, what are the shortest paths? Now from here to say here, you may say, oh, the shortest path is clearly there. But as you're moving around corners, you're definitely going to want to like cut the corner, if that makes sense, go through the corner. So that makes these corners the points of interest. And if you do that over the whole grid, suddenly there's only like a few hundred points, and now you can do Dijkstras on that, right? Because there's only a few hundred points, there's not billions of billions. You can now do a Dijkstra on it because there's only a few. I've only done a few here, but you can imagine like you're only interested in like the corners here, 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 right? And like here, 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 here. And then you just, because we're on a grid, you can just calculate the Manhattan distance, right? So the fastest solution, like from here to here, like say you've gotten to like this point right here, is obviously just like a straight line, right? And so it'll be like the Manhattan distance, and say that's, I don't know, 75 or whatever. You'll know that that's the distance you travel to get from there to there. And then that will say like, oh, this one to this one is like, 100 or whatever, 160 is what that looks more like. And now like the distance from here to the end is 160. I hope that makes sense. So again, I think it's called graph contraction or grid compaction. Some G word with a C word combined gives you what this is. And once you've thought about it a couple times through, I think it makes much more sense, because the idea is, you're saying, I'm not really, and we've had advent to code problems like this before, which was essentially the same, is like the grid becomes so large that it's much easier to just find like the points and the distance to those points, and then do Dijkstras on that thing, and then you can solve it. So that's like the intuition behind solving that, but behind solving part 3. And that's what allows you to go from something absurdly large like this to a feasible solution that won't consume 128 gigabytes of RAM. What does that solution look like? Let's go look at it. Like I said, I had to implement two more things for the point. We had to do the distance out, the Manhattan distance, right? So we want to do that, and I'm sure we've done this before. It's basically just you do the absolute value of the difference of the x's plus the absolute value of the difference of the y's, and that gets you the distance from 2 points, Manhattan style. Oh, I think it's also called taxi cab, right? And the idea is you're either going up, down, left, or right. You're never like going diagonal. So it's always like, to get from one square on the grid to another, it's always like 1, 2, 3, 4, 5. That was a bad one. 1, 2, 3, 4, 5, right? Like to get you up here or whatever. Let's see. When we're doing the grid thing, I have this neighbors algorithm. You'll see me use it. It's just asking like, what are my neighbors? And the reason why I do this is to get the corners, right? So once I hit the end, of a line segment or a wall segment, I'm going to get all 8 surrounding neighbors, right? So just to be clear, like I'll just draw it down here to show up, right? So if I have this box right here, I need to get 1, 2, 3, 5, 6, 7, and 8. I want to get these 8 ones, and these are my quote unquote points of interest. Now, obviously, not all of them are going to be points of interest, right? Like if the wall goes down here and then it turns this way, like this one and this one's not a point of interest, but like these ones are, and I can calculate these ones, right? So that's how I'm creating my like points of interest. That literally just did I accidentally draw that hand? I think I must have clicked something. Anyway, so that's me getting the neighbors, right? I'm going to go do the Cartesian product of -1 to 1 with -1 to 1. I'm going to filter by, I don't want the 0th one because that's where I'm currently at. And then I'm just going to convert those into a point. One thing that I noticed is I used to do a lot of collecting. I would collect these points and then iterate over them. It occurred to me, I think, when I was reading some code from a previous few days, you could actually just return an iterator here, which I think is cool, right? So I haven't collected this iterator, but I can return an iterator that returns a point. And now I don't actually like quote unquote create the vector data structure to like pass it. Maybe you want to keep the points for some other reason, and so that makes more sense. Okay, and then the rest of it is drawing the map, right? And so I created a data structure here called a map, which I thought hopefully would help make it simpler to understand. So what do we need for our map? We need to know where we start. We need to know where we end. We need to know where the walls are, and we need to know what are the points of interest, right? What are the corners, the points of interest on those corners? And then given that, I could, given those 4 things, I can run Dijkstra's. So we can actually look at my part 3 solution. Capital D there. I just create my map that has the start, the end, the walls, and the Dijkstra's. And then I use the pathfinding crate to run Dijkstra. So I start at start. My neighbors function is map neighbors from. And my end state, I don't know if you remember, but Dijkstra's returns are what it asks for you is your start location and then 2 functions. The first one is to get your neighbors, and the second one is, are you at the end, right? So if I'm at the end, it's just where that pause is map.end. And then it returns the actual path plus the cost. We're only interested in the cost, so that's what we return for part 3. So that looks kind of like magic, right? The harder part, and what took me the longest time, was actually getting this information, right? It's like, how do we well, start point's relatively easy. End point also is arguably easy because it's just the last point of the last wall segment. But then you have to build the walls. I did segments, so it's like a start and an end point. And then the points of interest, again, just a set of points, which are those corners that I'd be interested in doing. So how do we do that? Well, I build a map from the input, right? And the way to think about this is, when I was building it, like the thing that made it easier to like reason about it is I mean, I guess maybe it's not that difficult. If you look at this code, it's actually not much different than like this code up here, because you're essentially like turning and then updating your state. The one thing you had to think about right here is like, where are your segments? Where are your like line segments? How do they go? And that's why I have like this dist -2 in here. Like obviously I'm at the start position. I don't want to include that in my wall. I actually want to include the next one right here. And then I want to include all but the last one, like right here on this side. And I'm going to consider that the line segment. And then when I go again, I'm going to like move it like one more, and that's going to be my start for the next line segment. And then like say this one comes up this way, I'm going to go up there. So that's why I have the -2 here. But I thought doing it this way made it compact enough that it was reasonable. Basically, I'm going to update my delta by turning. I'm going to move to my next position by incrementing my delta. That's going to get me like up 1. Then I'm going to set my like the start of the wall to my current position. Now I'm going to move to the end position, but obviously I'm going to do it -2 because remember at the beginning I moved 1, and now at the end you'll see I'll move 1 more. And this is because I'm interested in getting the corners, right? So, but at that point I now have my wall segment, and so I just do walls.push, right? This works. I think it looks cleaner than the other solution I had. I had a bunch of if blocks and if else's. This one felt like it looked cleaner because but to be clear, it only kind of works because you can only go up, down, left, and right, if that makes sense. And so the Manhattan distances and the wall intersections happen to be equal. I guess the walls are still there is the way to think about it. It just, this code looks a little funny because you like step once and then you set that as your start, and then you move everything but 2 because you've already stepped once. And then you add that as your wall segment, and then you step once more, and that is your corner. And again, the reason I'm doing this is because it's allowing me to like see where the corners are and map my points of interest around those corners. So I would never actually go to that point, but it allows me to know like that's the corner, and my points of interest are the ones that are around there. At first, I had a little bug. I was also building my points of interest based on this, but you actually have to wait until you've built all the walls. I can't remember why that was. Maybe you don't actually have to anymore. I had some concern, like, I don't think you can see it very well in this map because it's absurdly large, but I think there's some places where they don't technically intersect, but they like overlap, meaning like this would never be a solution right here. I don't remember if that, anyway, I don't remember. I was having trouble trying to get to the right like thing, and I found that it's easier for me to like build the walls and the corners, and then once I've done that, I can calculate the points of interest. But what are the points of interest? Well, I've collected all my corners, so I just say give me all the neighbors, and then I filter it by is it a valid move. This is it a valid move, I'll show you later, but it's basically saying, am I not in a wall? Would I not intersect a wall? And because I just want a single point, I do the 2 directions. This is like an intersect algorithm that I do, and I'm saying, okay, I'm going to go over this point. Does it intersect with any of the walls? That's the equivalent. A line segment at the same position is just a point. So I say, does it intersect? And then I needed to include start and end with this, right? Obviously, I want my start and end as points of interest. But now I've got all my corners and I've got all my points of interest. And we can I actually don't think I did this. Uh-oh. So now there's only 1,500 points of interest, right? A much easier algorithm, and you're not going to use most of them. But there's now it's like a much easier algorithm for you to say, how do I reconcile? Because now, just to be clear, you're now saying I only have to run Dijkstra on 1,500 points, right? So that's what turns it in from a intractable, use up all the memory on your computer problem to a much more like solvable, oh, this is how we solve this problem. I hope that makes sense. So now that we have those, that I just had two other neighbor functions, right? The question is, what are my neighbors of points of interest? And it's actually all of them. This is maybe not the most efficient way, but I literally say, what are the neighbors of my points of interest? This is what I'm passing as my neighbors function to Dijkstra. I actually say all of the points of interest, where, you know, obviously I don't want my from and my to be the same, but it needs to be a valid move, right? It can't intersect. And then I need to include the distance from those. So that's where the Manhattan distance comes in. This function expects you to return the next point, or like the next, you know, the next point of that would be a neighbor. They don't call it a neighbor, huh? They call it successors, I think, in in the pathfinding crate. So you want to find that neighbor or successor, but you also have to return what is the distance to that neighbor, because they use like it might be something different, but it's like a min heap, right? So you're always tracking like what the lowest distances are and traversing those first. Anyway, so that's my neighbors function. It feels, this is what I'm saying, is like I spent a lot of time iterating over this, and it feels to me like it became much more reasonable when I broke these things up, right? I want to collect all my corners. I want to gather my points of interests. Here's a simple function to find my neighbors. And then the last function is, and this one feels like the worst one, I haven't found a great way to do this one, is it a valid move? And we're just checking bounding boxes, the way to think about it. Like you have a from and a to point, and then you have the wall. The wall happens to be a line, but it works the same way. Is you're just checking, do two rectangles intersect with each other? And so like, again, like what does that look like? Like imagine you have a wall like this, and I want to go from this point to this point. Well, I just draw, I just like sort of draw this fake rectangle and say like, do those intersect? And then if they do, you know, I can't go from there to there. That makes sense. This actually isn't a great example, but you get the idea. Like, obviously I can't go from there to there because like these two rectangles intersect right here. And so that's what this is basically doing, is I'm getting the bounding box of my 2 points, and then I'm getting the bounding box of my wall, and I'm just asking myself, you know, are the mins and maxes causing them to overlap? And so you're either going to get two cases, right? You're going to get this case where they do overlap, or you're going to get a you know, like this to this. That's not going to overlap, right? Because it's going to kind of draw this box like this. Those won't overlap, so you'll be okay. That's all that's doing. I did try using, there was another one that I found online that was like a CCW. It didn't actually work here, and I don't know why that is. So if there's someone that's more mathy that might know why it didn't work, that would be great. Is that enough explaining? Because that's literally it. Again, just at a really high level, the idea is don't deal with the whole grid, like one grid point at a time. Find the points of interest and run Dijkstras on that. So for me, finding the points of interest was drawing the wall and keeping track of the corners, and then adding the neighbors of those corners as points of interest where they were valid, right? Obviously, we didn't want to include points of interest that were wall. That led to only like 1,500 points to test in Dijkstra's, which was substantially easier to solve. Then it's just a matter of saying, like, how do you determine what's a valid move? Meaning, would going from point A to point B intersect? And then you need to know who are my neighbors, right? So in my case, I said try them all as long as I can get from one of them to the other. And yeah, I think it runs fairly fast, right? 45 milliseconds, and you know, you get an answer pretty quick. Much easier to solve and grok in my mind. I didn't print it out originally, but I had done some work to try and like shrink this down. It didn't look good though. So I got rid of it, and I got AI to write me a Python script that uses like matplotlib, I think, to like plot this thing. Um, so you can, it's right here. I don't know if I'll include the link or not. Can you include a PNG in the thing? Anyway, but it had this Python script that it created for me that did it. And so this makes it, at least in my mind, visualizing it helps a lot. I tried to visualize it in the terminal, but especially like with this font, with like, you know, I try and zoom in so it's more readable. It made it really hard to understand. Anyway, there you go. That was the day. Should we go look and see how everyone else did? I suspect this problem was a little bit harder. I had a lot of time. We can go check my time. 2 hours. Yeah. I mean, that's probably about right. That again, like the first hour, I think I was like doing things off and on. So maybe this is about a half an hour short, but 2 hours seems 35. Okay. Yeah. So it probably was kind of hard, or maybe you all have lives and I don't, and I happen to get a better score on this one than the other days. Because that does feel like I don't think I've gotten that. Oh, I did a 31. Yeah, not nearly as good. Speaking of which, obviously next week is the holidays for where I live, and so I actually don't know what these last few days look like. I think a couple of the days I can probably do right on time, and so the video will come out regularly. But I love me some Thanksgiving food, so these days. Anyway, yeah, 2 hours again. So compared to the last few days, definitely more complex. We don't talk about day 10, um, day 9 and 10. Yeah, so it does feel like it, at least for me, it felt like it was a little bit harder problem because I almost immediately recognized as my 128 gigs filled up, oh, I'm gonna have to simplify the grid. And again, grid compaction, graph contraction, I don't know, whatever it is. I recognized, oh, I'm probably gonna have to do that. And it was just a matter of like the time was, can you figure out how to do that? And I'll admit, my code looked a lot uglier after I had solved it and, you know, got to my 2 hours and done. I've since spent a couple hours like cleaning this much more up because I think the readability helps with this one, right? At least in my mind, really understanding what it was doing distilled in my mind what is happening so that, you know, when it comes up again, I can remember. And I think the corners one probably is a valid way to solve it for most things. I have not ever done the X's and Y's one. And so maybe it would be, I presume what you do is you just, maybe it's not actually that hard. I mean, I have all my corners, and so those are my X's and Y's. And so I just like do a Cartesian product of all the X's and all the Y's. Maybe it goes from like 1,400 corners to like, or 1,400 points of interest to like 2,000. But I mean, I can't imagine how that makes it worse or better. It's substantially smaller, and so I'm sure it solves in time. That if that makes sense. So, do we cry about how fast some people solved this? Just for day 15. 15 minutes. Okay, well they used AI, so they don't. That's actually really strong. And so Jonathan Paulson, he's a competitive programmer. He does really good. Doing that in 15 minutes is or 50 minutes is probably pretty huge. And technically got first place. I don't think you can. In fact, I'm gonna. I don't have, again, I don't have a problem with you using AI if you're using AI to solve these. I think that's great. That's how you do it. There's definitely days when I haven't known how to do something and I've gone and researched. And just to be clear, like at work, 60% of the code I write is done by AI, right? So I do a lot of interactive. What I like about puzzle solving is it's me doing my own coding. If that makes sense. These times are quite impressive, I think, for this type of problem. But it does go to show you, like, it was quite a hard day, right? So, very cool though. Yeah, these I suspect like getting to the end of the leaderboard. I assume these ones are just multiple days, right? Like couldn't do it, came back the next day and finished it up. So a much harder day, at least in my mind. And maybe this is their thinking is like, oh, we'll give them a weekend problem that they can mull over and solve over a few days. I think that's great. That's really cool, right? The ones that I really hate when it's like a Tuesday and it's all like, this is going to take you 3 days to solve, because then it feels like you're like 3 days. Anyway, let's go look at some solutions. What do we got? Language, Rust. One problem today, we build a compressed graph. Maybe that's what it's called, graph compression. For each wall, add the x coordinates before and after and the y coordinates before and after. Okay, so you're adding like, I think that is kind of like the corners. Then Dijkstra BFS over this compressed graph, rejecting the pass-through wall. Is that actually true? B tree. Why would you use a B tree? Do they use rain? Okay, so like a B tree is like a um, it's like a hash set, but it tracks it in a tree structure, which allows you to more easily do like ranges. So as opposed to just asking yourself, am I in this is this value in the set, which is kind of what a hash set is meant to do. A B tree set allows you to say things like, give me everything within this range. But I'm not seeing where they're doing that. So maybe they originally did it that way, or maybe I'm just not reading. But it looks like they are using the X's and Y's, right? And again, I would have to spend some more time grokking this. I think the idea is you're like finding points of intersection, and then so like you're drawing like you're saying, oh, this line right here at this y position, or this line right here at this x position is interesting, and then you're going to do that for all the x's and all the y's, and then I did that the wrong way, right? All the y's and all the x's, and then you're going to, wherever they intersect are going to be your like quote unquote points of interest. It appears you can shrink it too, is what this is suggesting. How do you like unshrink? I guess you just track the cost, the original shrinkage. Is that right? I actually don't see why they're using it. I mean, again, maybe it's just they had started using it, stuck with it. That's oh, maybe I'm missing some stuff because it looks like they have some of their own pre-implemented stuff. Like it's not a self-contained solution. Yeah, this is the key right here. I think this is the thing. Definitely a lot of discussion on this one. Good. Uh, uh, very good. Very cool. You look at this solution. Another one in Rust. Durs. So this is where you're turning. These are the walls. So your start and end point. Again, I think my original solution sort of looked like this. I was using eye sizes, I think. First mapping left. Yeah, they are intervals between X and Y. But you could store them as ranges, because I think in Rust, the ranges, you can do things on them, right? You like contain, stuff like that. They'll do the work for it. Okay. First two parts easily. The third part was a real challenge. Too many bugs. Yeah, I think that's this is definitely a problem where it could take you multiple tries, and sometimes it's easier to say, "Oh, I gotta restart." Split at. Oh, that's cool. Okay, that this is not the C++ I remember. Is this like a hint to the compiler? So when it's doing its branch prediction, it's like you're pre-hinting it. That's cool. Okay, they are creating a point. Directions. Yeah, it looks like this one's doing the X's and Y's too. So maybe it's something I ought to just look at and see. It's possible that it's more efficient than my solution. I actually don't. I feel like mine's more readable, but that could just be me. I solved part 3 of the problem more or less by hand since the BFF couldn't handle it. Oh, that's actually cool. If you like draw the graph yourself, yeah, I could totally see you saying like, "Oh, here's how you go." Interesting. Yeah, if you were able to like draw this in like a with like matplotlib or whatever, or an SVG is kind of cool because then you can zoom in and zoom out. You can kind of like put these things. It might be very easy for you to say, "Oh, I'm going to go here, then here, then." That's actually not bad either, right? I think I've shown you before. Some people solve this stuff in um, like using Excel. I don't know how you'd solve some of these in Excel, or some people print it out and solve it by hand. That's awesome. Go for it. I think that's cool. Whatever you're doing to like grow and learn, I think is really cool. This is an interesting thing. It looks like some people discovered that they couldn't do Dijkstras on it, and so you can just BFS the compressed grid. I guess maybe you know enough about the grid that you can say, and that's totally a valid solution, right? Is to say, oh, if I look at this, I recognize some specialty in this. Like I didn't even look. It's possible too. I mean, maybe it's not. These numbers look very random, but it's possible to say, oh, they're all divisible by 5,762,422, right? Like you could do like greatest common factor or something like that, and extract, and then maybe the grid becomes substantially smaller to get to the same answer. But it sounds like what some of these solutions are saying is you can compress the grid without having to worry about that. Yeah, I suspect what that commenter is saying is like this work. So if you think about essentially what's happening is like they're mapping, like they're taking the thing and then they're like shifting it all in to making it fit, and then they're tracking, like, you know, how does one if you're going to this point, it's actually this point in real space, so that when you do your moves, when you do your BFS, you know that, like, oh, if I've stepped from this point to this point, it's actually a million points. Does that make sense? I hope that you understand what that's saying. I understand what it's saying. I think that's what this is doing. Is it saying, oh, I'm going to like create an equivalent smaller grid. I'd be curious. This is the second time I've seen a B tree set, but I can't tell what they're using it for. Yeah, I was like, so you can see now they're doing the BFS, but they return their new positions, but they also return like the, like, quote unquote real positions, like, and so that gives you like the actual distances. Again, it doesn't work. Again, like, I think there's like it doesn't work in the general case, is what this person is trying to explain. Um, uh, but you feel like it's okay. It sounds like based on the input, it's okay to do that. So, interesting. And mine's not. Mine's definitely in the milliseconds, but this one's potentially twice as fast. What are they doing? Coordinate compression. Okay. So it would be interesting to know, am I the only one that did the corners thing? It looks like everyone else is just compressing the coordinates, solving it. Interesting. Oh, this is cool. I think I've talked to this person before. They're doing it in GD script, which seems really cool. But yeah, they probably don't have a min heap, and so you have to like create your own. But that's cool to implement Dijkstras. So again, we've done Dijkstras before, so that's why I kind of use the pathfinding library in Rust. Obviously, you don't have that here. So just an idea of what you do is you want to have some kind of min heap or something that's like, what's the next unvisited node, or I should say, what's the next frontier that I should go visit, and you always want to pick the one that currently has the shortest distance. And that has the effect of eventually you'll hit the end and you'll know you got there in the shortest distance. So you use a min heap, but otherwise it's a BFS where you just like push items onto the queue and pull items off and then process them in the same way you would do a BFS. It's just, instead of using, like, I use a vec deck, you're now going to use a min heap for it. Oh, I should say your scene is different too, right? Because your scene is not just the position that you're in, it's like the position and the distance you've gone, because you might later find it's probably not doesn't ever happen in this case, but there are, you could imagine a case where like you're doing shortest paths and like you get to here, and like these paths all are like, I don't know, they add up to like 73. um but now you get one that's like uh 70, like this one's 70 that you've gotten here. And so you do this one, it says 73. Now you do this one when you're at 70, and this one is only one, so the total here would be 71. And so you now say, okay, well now I know this was the shortest path, but this is like the new shortest path, so I'm not going to use that one. That's the only like extra special thing you have to account for when you're doing that kind of thing. Okay, this is a fun one that I think would be fun to explore more, because it's clear that there's other types of ways to do like grid compression. And so I think it would be a fun one to explore and learn more about, just so I understand exactly how it works. I think I understand like the intuition behind it, right? Is like this line right here can clearly be compressed, and this line, these two lines can clearly be compressed down. And so you no longer have this giant amount of empty space, and that allows you to do Dijkstras on like a much smaller grid. You just have to remember that if you're going from like the new compressed grid would have you go from here to here in one step, you just have to recognize that the real value of those is 5,764 or whatever. And again, there's probably, it sounds like there's some gotchas there that I just don't know enough about. And so again, I think for me, the way that I solved it is a little bit different. And this one definitely works in the generic case, right? Is like you're building a wall, you're keeping track of those wall segments, and then you're also tracking like what are the points of interest as you take those corners. And that, I think this should solve it in any general case. Although I do have a lot of unwraps and stuff here that are probably going to break for certain walls, right? Like I don't think, because of the way the problem is designed, there's a way for you to like not have a solution, but you might be able to, you know, do some weird inputs that might cause. Anyway, fun day for me. I had a lot of fun. It was great to solve it. Especially again, I think for me, this was a day where I'm like, I quickly kind of knew what I wanted to do, but I don't think I'd ever done this before. Like, well, I've done it before, but it's been a long time. And so it wasn't quite clear to me. I had to like refresh how I do all this stuff. And so that's why I spent a lot of time refining the code. Hopefully this will make more sense to you, and the solution, will kind of help you understand the intuition behind how I solved it. And, um, so you'll be better able to solve a problem next time. I feel like I will. I think these type of things are common enough that I wouldn't be surprised if something like this shows up in Advent of Code. So again, we only got 5 more days left of Everybody Code, and then we're moving on to Advent of Code, and I think that's only like, what did they shrink it down to? 12 days, 15 days. I don't remember the exact number. It's not all the way to the holidays, the 25th, Christmas. It's just, I think it's 12 days, is what they said. Anyway, it's much shorter, so but we'll be going from one to the other. Anyway, after that though, let me know what you want to do. I'm happy to go back to Everybody Codes and finish the unfinished year. They also have these stories, which looks like they're like mini little things, and people are definitely like solving these. So I think there's like, yeah, there's just it's a fewer number of quests that you have to start. And like the idea is like to solve the quests and things like that. I'll play with that. We can also go back to solving more Advent of Code. I think we've done 2 years now. In my actual, I think I'm logged. I think I've actually solved, oh look, I'm like 2 years behind. I'm missing these 2 years. This is my actual one, my actual account. When we solve 2025, I'll solve it on here. But I have another account that I'm using for our new Advent code, and I think we've done these 2 years, so that'll be fun. Some of these coming up the next few years, I haven't solved at all, so that'll make for some interesting solves, especially if I haven't done it before. But I definitely feel like I'm growing and getting better, and I hope the same's happening with you. So that's all to say. I have a lot of fun doing this. If you have thoughts or ideas on how to improve, or you found a cool algorithm to work on, or maybe you have a question, send it my way. I'd love to work on it. I'll also be checking the Reddit. So if you posted your solution on Reddit, let me know, and I'll be sure to check it out. Thanks, everybody. Bye.